This video contains the solutions to sample exam number 3. For this first question, we're given a function and we're told that there are critical points at -3, 12, 5, -18, and an inflection point at 2, 1. And based on that information, we're trying to figure out which of these graphing windows would be a good window on which to graph the function. So certainly, any window that we would want to think would be a good window should include all of these interesting points. So when we look at option A, we see that in the y-coordinate, it only goes from -10 to 10, which isn't going to be big enough to include these two interesting points. So we can eliminate option A. For option B, the y value only goes from -18 to 12, which is exactly the y values of these two interesting critical points. And that's not going to be enough to be a good window because the interesting behavior is going to be right at the edge of the screen. We typically want to have a little bit of wiggle room around those points, so we can eliminate B as well. C looks like a good option because the x value goes from -5 to 8, which includes all of the x values that we care about with some space around them. And then same for the y values, -25 to 15, again includes all of the y values that we want with some space around them. Now D is way too big. It's the x and y values there are so far away from the x and y values that we actually care about that any interesting behavior is going to be very tiny on the screen. So D is not a good option either, and so the best answer here is C. For number 2, we want to know which of the following functions is a solution to the initial value problem f prime of x equals 2x and f of 4 equals 10. A quick glance at the options shows that all of these satisfy the first part of that initial value problem. All of these functions have a derivative of 2x. So then the only question becomes which of these has the property that f of 4 equals 10. Plugging 4 into each of the options, we quickly see that A is the only one that has that property. Moving on to number 3, if we've got the sides of the square changing in length, that causes the area to change, and we want to have the related rates relationship between the rate at which the area changes and the rate at which the side changes. So what we need to do is take this area formula and implicitly derive each side with respect to t. When we do that using the chain rule, we get option D. For number 4, we see that we're assuming that f is continuous at C, and we want to know which of the following statements is not equivalent to the others. So that means 3 of these statements are all equivalent to each other, and one of them is an odd one out. So having a local maximum is the same as the derivative changing from positive to negative, and that's also the same as the function changing from increasing to decreasing. So A, B, and D are all the same. And if we look at C, saying that f is concave down, that's not enough to say that we have a local maximum, because a function can be concave down, for example, it could look like that, and never have a local maximum, and it certainly wouldn't necessarily have to have the local maximum at that same point C. So option C here is the one that is the odd one out. Moving on to number 5, we want to know for which value of x does f of x equals x squared have an absolute maximum on the interval from -3 to 2, including -3, not including 2. So this graph is going to look something like the parabola starting at the point -3, 9, and going through to the point 2, 4, where we'll have an open circle. That open circle will be there because of this round parentheses. That means that the number 2 is not included in my interval. So the absolute maximum, the highest y value that we would have on this function, is going to be right here at x equals -3, and so B is the answer that we're looking for. For number 6, we want to know for which value of x does f of x equals x squared have an absolute minimum on this interval. So it's the same graph, we want to know where the minimum is, and that is going to be the lowest possible value of y, which is going to be right here at x equals 0. This is the point 0, 0. So that's where my absolute minimum is, and so the answer is D. Now in this next section, we're answering some short questions based on graphs. And the tricky thing about this first one is that what we always have to keep in mind is that the graph that we see here is the graph of f prime. This is the graph of the derivative. The number one mistake that folks make in these kinds of problems is forgetting that this is the graph of f prime and then answering the questions as if it were the graph of f. So if we look at part A here, we're asked on which intervals is f of x increasing. So that is not asking where is this graph that we see increasing, because this graph that we see is f prime. If we want to know where f is increasing, what we need to realize is how to translate that information from a question about f to a question about f prime. So f of x increasing, what we have to remember, means that f prime of x is positive. And so what this question is really asking is, where is this graph that we see positive? And what we can see is that it's positive from -2 to 0 and from 0 to 2. So our answer here would be -2 to 0 and 0 to 2. And now you might be wondering, well, why can't I just skip over that? Why can't I just combine those together and say -2 to 2? Well, the problem is that here at 0, the y value is actually 0. It's not positive. 0 is not a positive number. And so this function is positive from -2 to 0, and for a split second, for an instant, the y value really reaches 0, and then it returns to being positive. And so this function is increasing from -2 to 0 and from 0 to 2. For b, we're asked to list the critical points for f. Now, this is going to be the place where the derivative is 0 or undefined, the derivative of f. But the graph of f prime is the graph that we see here. So what we're looking for is, where is this graph that we see 0 or undefined? So in other words, where is f prime equal to 0 or undefined? So the graph that we see is 0 here at -2 and here at 0. And so those would be my answers, -2 and 0. Last question, on which intervals is f concave up? And again, what we have to do is translate this question from a question about f to information about f prime. And so what we should remember is that f is concave up if and only if f prime is increasing. So where is this function f prime increasing? Well, it's increasing from -3 to -1, and it's increasing from 0 to 2. So that would be my answer here, -3 to -1, and 0 to 2. So for all of these problems where you're given a graph of f prime and asked questions about f, we always have to translate that question into the language of f prime so that we can look at the graph that we have and use it to answer those questions. Now for this next one, this is a graph of g, and so if we're asking about g, then this is the graph that we're looking at. So for part A here, at which labeled points does g have an absolute maximum? That's what we're being asked here. This is g, where does this function have an absolute maximum? In other words, where does this function reach its highest possible value? And we see that that's going to be here at p, because at that point, that's the y value where we never get any other higher y value. So the answer here would be p. For part B, at which labeled points does g of x have a local minimum? So that's a place where it reaches a low point, not necessarily the lowest point, but a low point. And that would be here at q, and that's it. B would not be an answer because, if you remember, when we think about local maximums and local minimums, we don't include endpoints in that. So A and B are not local minimums, only Q is the correct answer here. And then for part C, in which intervals is g of x decreasing? Again, this is g of x. So when is this function decreasing? Well, it's going to be from P to Q, and then from R to S, and it looks like at S the slope zeroes out, and then it would be from S to B. So my answer here would be P to Q, and then R to S, and then S to B. And again, we can't combine the R to S and the S to B and just say from R to B, because at that split second, at S, the slope is 0, and so the function momentarily stops decreasing before continuing to decrease. So that would be my answer for part C. All right, so now we've got some application problems. These first two problems are related rates problems. So for this first one, we're told that the radius of a circle is decreasing at a rate of 2 inches per minute, and we want to know the rate at which the area is changing when the radius is 10 inches. So we're given that A equals pi r squared, and we want to use that to answer our related rates problem. We're also given that the radius is decreasing at a rate of 2 inches per minute, so that's dr dt equals -2 inches per minute. And the question is, what's dA dt when the radius is 10 inches? So we use our related rates, we take the implicit differentiation of both sides. On the left-hand side, the derivative of A is dA dt. On the right-hand side, pi is a constant multiple, and the derivative of r squared is 2r dr dt. So now we plug in what we know. We're given that dr dt is -2, we're given that r is 10, dA dt is what we want, and so we just plug in. So we get that dA dt is pi times 2 times 10 times negative 2, which is negative 40 pi, and the units here would be square inches per minute. We throw that in our calculators to get our approximate answer, and the approximate answer would be negative 125.66 square inches per minute. Next up, we've got a surface ship moving horizontally in a straight line at a speed of 10 kilometers per hour, and at the same time, an enemy submarine maintains a position directly below the ship while diving at an angle of 20 degrees below the horizontal. How fast is the submarine's altitude decreasing? So here's the surface, where the surface ship is traveling, and then below that, the submarine is diving at an angle of 20 degrees. So this angle is 20 degrees. So here's the surface ship. I'm going to attempt to draw a boat. There you go. And then here's the submarine underneath it. And so what we're interested in is the rate at which this altitude, essentially the depth of the submarine, is decreasing. So how do we use the fact that the ship is moving at a speed of 10 kilometers per hour? Well, remember that speed and velocity relate to the derivative of position. And so we can think of this position of the ship, s, and say that the speed being 10 kilometers per hour is just telling us that ds dt is 10 kilometers per hour. dA dt is what we're looking for. And so this is the situation that we have. Now, what's going to be the relationship between a and s here? Well, if you're thinking the Pythagorean theorem, that's not really going to be a good idea here because we don't really know anything about this hypotenuse. They don't tell us anything about that hypotenuse, and they don't ask us anything about that hypotenuse. So if we can avoid introducing a new variable that we don't know anything about, then that's a good idea. And we really want to use the fact that we've got this 20-degree angle here. So if we think about trigonometry, we can set up a trigonometric relationship that says the tangent of 20 degrees equals opposite over adjacent, which would be a over s. Now we could launch right into taking a derivative here, but the problem is they don't actually tell us any values of a or s. So if we start with what we've got right here and use the quotient rule, we're going to get some a's and s's that we're not going to be able to plug into. So the clever idea here that we have to use is to multiply both sides of this equation by s before taking the derivative. Not only does that let us avoid the quotient rule, it also alleviates the issue that we don't actually have values of a and s here. So now when we take the derivative of both sides, the tangent of 20 degrees is a constant multiple, the derivative of s is ds dt, and the derivative of a is dA dt. dA dt is what we want, ds dt we're told is 10. And so notice that doing it this way, we don't have any a's or s's that we need to plug into, which is good because we don't know what to plug in for those. So the exact answer that we get is dA dt equals 10 tangent of 20 degrees, and the units here would be kilometers per hour. And throwing that in our calculators, we get an approximate answer, which is 3.64, and again, the units would be kilometers per hour. All right, now we've got some application problems, and these are optimization problems. First thing to note is that on my version, there was a typo that I hadn't fixed yet. So on the one that you have, this says small, which is what I meant to say. So it should be, we want to find two numbers with a and b with sum 50 that have the property that a squared plus 2b is as small as possible. That's what it says on your print copy, but like I said, the version I was using had a typo here. So we've got this fact that the two positive numbers have sum 50, and that's our constraint. This tells us that the constraint here is that a plus b has to equal 50. And our goal is to minimize the value of a squared plus 2b. So I'll call it v for value. But a squared plus 2b, that's the thing that we want to make as small as possible. So we're going to use our constraint to eliminate one of those two variables. I'm going to go ahead and solve this for b. I'm going to write it as b equals 50 minus a. And when I substitute that in, I get a squared plus 2 times 50 minus a, which gives me a squared plus 100 minus 2a. That's the value that I'm trying to minimize. Now that I've got it expressed in terms of one variable, I'm going to take the derivative of both sides. I get 2a, the derivative of 100 is 0, 2a minus 2. Now I'm looking for critical points. 2a minus 2, set that equals 0. Solve, I get 2a equals 2, and a equals 1. Now I want to make sure that this really is the minimum that I'm looking for, so I'm going to test this. I'm going to use the second derivative test. I'm going to take v double prime, which is just 2. The derivative of 2a is 2, minus, and the derivative of 2 is 0. And now when I plug in my critical point, I plug in 1. Well, there aren't any a's to plug into, so I just get 2. And since 2 is positive, that means that we have a local min. Another way to see why this would be a minimum is that this is a parabola, right? It's positive value of the coefficient of a squared, and so this is a right side up parabola, and so the critical point that we get really is a minimum. So the answer to the question, which two positive numbers? Well, a would be 1, and b would be 50 minus a, 50 minus 1, which is 49. So those are the two numbers we're looking for. All right, last one. We've got a rectangular flower garden with an area of 30 square meters, is surrounded by a grass border 1 meter wide on two sides, 2 meter wide on the other two sides, and we want to know which dimensions of the garden maximize the combined area of the garden and borders. And actually this one also has a typo. It's not actually maximize, we actually want to minimize the combined area of the garden and the borders. So when we're told here that the area of the inner garden is 30 square meters, we can think of this as telling us that the length of the garden, which we'll call L, times the width of the garden is going to be 30. So that's our constraint. Our constraint here is that L times W has to be 30. Now what's our goal? Our goal is to maximize the area of the entire garden. So the area of the entire garden is the length of the full garden, which is going to be the L in the middle, plus 2 on each side. That's going to be L plus 4. And the width of the entire garden is going to be the width in the middle, plus 1 at the top and 1 at the bottom. That's going to be W plus 2. So that gives us L plus 4 times W plus 2. When we multiply that out, we get LW plus 2L plus 4W plus 8. Now using our constraint, we can eliminate W by rewriting it as 30 over L. So that gives us L times 30 over L plus 2L plus 4 times 30 over L plus 8. And that simplifies a little bit to 30 plus 2L plus 120 over L plus 8. So that's our objective. That's what we're trying to, in this case, minimize. So when we take a derivative, first thing we're going to do to make our derivative a little bit easier is think of 120 over L as 120L to the minus 1. So we take our derivative. Derivative of 30 is 0. Derivative of 2L is 2. Derivative of 120L to the minus 1 is minus 120L to the minus 2 by the power rule. And the derivative of 8 is 0. Now we look at that derivative, and we can rewrite it without the negative exponent to make it a little bit easier to understand. That's our A prime. And we look at that and we say to ourselves, all right, where is that undefined and where does it equal 0? Well, it's undefined when L is 0. But if we think about this, the length of the flower garden cannot be 0 because then the area wouldn't be able to be 30. Area is length times width, so if the length were 0, the area would be 0. So 0 isn't in the domain of this function, which means 0 is not a critical point. The derivative is definitely undefined at 0, but since 0 isn't in the domain, that makes it not a critical point. So we set this equal to 0 to search for other critical points, and we solve. Add 120L squared to both sides, multiply both sides by L squared, divide both sides by 2, take the square root of both sides, we get plus or minus the square root of 60. Now negative the square root of 60 can't be the critical point that we're looking for because the length of the flower garden cannot be negative. So we eliminate that negative, and so the only critical point that we find is the square root of 60. Now we need to make sure that that's really the minimum that we're looking for. So we can use the first derivative test, put square root of 60 on a number line. We know that A prime is 0 there, so we pick a number less than square root of 60, pick a number bigger than square root of 60, plug those numbers into our derivative. So something less than square root of 60, how about 1? So A prime of 1, that's going to be 2 minus 120 over 1 squared, that's going to be negative 118. And something bigger than the square root of 60. The square root of 60, if we throw that on our calculators, is about 7.7, so let's try 10. So A prime of 10 works out to be positive 0.8. So what we see is that my A prime changes from negative to positive, which is what we would be looking for with the first derivative test, which tells us that we have a minimum. So we found the minimum that we were looking for. Now the only thing left to do is to go back and make sure that we answered the question. The question asks what dimensions of the garden. So knowing that L has to be the square root of 60, that tells me the length of the garden. It doesn't tell me the width of the garden. So it's going to be square root of 60 by whatever I get for W. So coming back to our constraint, we get that W would be 30 divided by the square root of 60. And that's going to be my width. Now if we want an approximate answer, we just throw that in our calculators and calculate. The square root of 60 rounded to 2 decimal places is 7.75. And the units here are meters. And then 30 divided by the square root of 60 works out to be about 3.87 meters. So there's our exact answer, and there's our approximate answer.